let's spend some time discussing the population mean estimation. The population mean y by u is defined as what is the mean? Mean is total divided by size, right? Population size. And so this is total, and this is the size, population size. So this is a parameter, and from the sample, so we only, so this one is for the whole population of the TI, right? This is the whole population of the clusters, so MI. So instead of the whole population, we only have a sample cluster. So the summation here is not just the population level, but on the sample level. And so the T hat is using the formula for the cluster sampling, right? And hat summation SI MI. Okay. So then we divide by these two. That exactly becomes then that means, okay, not to be confused, we can this is more rigorous. Okay, so that is the ratio, and then you can see that the numerator, the constant term, cancels. So that's why you get you obtain this estimator, right? So this is your estimator. Okay, so if mi's are all equal, then basically m can go outside. So mi's are all equal, then ti is equal to mi y by u, and mi's are all equal, then m times y by iu. So m cancels. Okay. So let me write it differently. So ni times m over y by summation I equal si m times y by iu. So m cancels. So 1 over ni summation I equal si y by iu. Okay. So that basically is the formula for this mean estimator. So in this case, the denominator is, so ni is fixed. This is fixed, but this n itself is random. So it depends on and ni's are all equal or not. We may have different ways of estimating the variance. Okay. So for the DOM example, mi's are all equal to 4. So that is a simpler method. So in that case, we have only to divide the total estimator by 400. So that's basically this one, 4.2. And for variance, we should divide it by 400 squares. So that gives the to the variance of the total estimator. So that is the this result. Now, more challenging case is when mi's are unequal. Okay, then denominator, this guy is random variable. So it's not fixed. Okay, random variable. So it's essentially ratio type estimator. So we need to apply the Taylor expansion. So we already studied how to apply the Taylor expansion for ratios, but let's do it review it one more time. Okay. So okay, so how, so now we can y bar r t hat divided by n hat. So let's write it as a t hat n hat. So that means if you write the function define f something like this, then it is x1 divided by x2, right? So how can we apply Taylor expansion to its expectation, which is this by where f1 t and okay, what does that mean? f1 x1 x2 means round x1 f x1 x2. So in this case f is x1 divided by x2, so if you differentiate with respect to x1, then it becomes 1 over x2. And f x2, if you define it as something like x2, then it is minus x1 over x2 square. Okay, so that means if you so this if you for this particular f, this one becomes t hat divided by n hat. This one is t divided by n plus n divided by 1 over n, and t hat minus t plus minus t divided by n square n hat minus n, right? So that gives the basically the formula. So that is y bar, and that is y bar u 1 over n t hat minus y bar u n hat. So that gives the that is this formula. That is the linearization formula here. So that is the derivation of this linearization. So that means the variance of this guy is approximately, so that is approximate equality of the 1 over n square times, okay, this is too thick, 1 over n square times variance of this guy. So t hat, what is t hat minus p u n hat? That they are n hat n1 divided by n small ni, summation I equal to si yi, oh no, sorry, not yi, ti minus ti minus y bar u mi. Okay, so that's this one. So that that is actually ti. So basically this is a estimator, unbiased estimator of summation of ti. Okay, under simple random sampling of clusters. So now you can basically, you already have the formula here. The formula is the total for clusters. You have the formula for total estimator. So now you have a formula. You just want to apply the formula to here. So that means, so my point is that variance of the y bar is 1 over n square variance of the ni I summation I di. And so on the simple random sampling, this is ni square sampling of clusters sd square, where sd square is summation the sample population variance of the di's. So that's supposed to be something like this, right? Using the formula for so basically this formula here is based on this part. So this part is used here to using di instead of ti. So now d bar u is 1 over ni I equal to 1 capital Ni di is the ti divided by m y by u mi, right? Mi. So that is 1 over ni t minus y by u times n if you apply the summation. So that is exactly equal to 0. So this part is 0. So that means you can directly write it as a di square. Di is ti minus mi y by u square. So that's exactly, so this one. Okay. And then because ti is mi times y by u, you obtain the same result. Okay. So that is the variance. And excuse me, for variance estimation, so it's the same story. If we knew di, if you can observe di, then we have only to use so here we have only to estimate sd square, sd squares by small sd squares, but we don't observe. So so di is ti minus y bar u mi, and the only thing we don't observe is this one. This is unknown. So how to obtain, how to estimate it? So we used ei, which is y bar, use a sample version. So that is this formula. So we use, so this part is the same as here. The only thing changes is estimator of sd square, and that is se, and then so this is estimator of ti equal to ti minus y bar u mi. Okay. And now if you do that, then the sample mean is exactly equal to 0, because the same story, ti minus y bar u mi, oh no, not y bar u, y bar. Okay, it becomes 0 by definition of the y bar. So you can simplify the computation, and so this one, the whole thing becomes ni minus 1 summation I equal si ei square, and then ei square is equal to this way, because ti is mi times y bar iu, right? So minus, so you can write it, let me write it carefully. You can write it this way, ei. So then you have mi square times this one. Okay.